Good morning and welcome back. So here we are in part C of chapter 14 with solutions. As we already know, solutions are homogeneous mixtures. If you have a mixture, at least you have two components. One of them is going to be the solute, the one in the lower amount. The other one is going to be the solvent, the one in the highest amount. And both of them combined is your solution, which is a homogeneous mixture. So it's common thinking then that we should be able to put numbers to this, and we're going to call this concentration. The more solute you have, the more concentrated the solution is going to be. So we're going to always measure the concentration, well, not always, most of the times, based on the amount of solute over the amount of the total solution. That's the traditional concentration. We're going to learn a new one called molality, not molarity, but molality, which is going to be amount of solute by kilograms of the solvent. So every other type of concentration is going to be over the solution. Molality is going to be the only one over the solvent. And we're going to use molality a lot on section D. So let's see how we're going to do this. So this is the objective we're going for. We're going to calculate concentrations, and we're going to calculate in terms of molarity, molality, mole fraction, percent composition, which is going to be given by 100%, or by million parts, or by a billion parts. It's mass of the solute over mass of the solution multiplied by 100, or multiplied by a million, or multiplied by a billion. Or it could be volume of the solute and volume of the solution multiplied by 100, multiplied by a million, or multiplied by a billion. So those are the main type of concentrations we're going to use. But once more, over 90% of the time, it's going to be the solute over the solution, which we have to realize that is the same as the solute over the solvent plus the solute, because the solution is nothing more than the mixture of them. So this factor is going to be very handy for us to utilize to solve a lot of problems, knowing that solution is the same as solute plus solvent in terms of the amount. So let's begin with this problem. A solution is prepared by dissolving 28 grams of glucose. So this is our solute because we are dissolving it in 355 grams of water. So this is our solvent because that's what we are dissolving in. In addition to that, this is 28.4 and this is 355. So the one in the highest amount is always the solvent. The final volume of the solution is 378 milliliters. So this is the solution, but it's given in volume. Calculate the solution concentration. Solution concentration is going to be solute over solution for most of them. And we're going to do it for the molality, the mole fraction, and the part per billions. So let's put this together. So my solute is 28.4 grams, and it's C6H12O6. My solvent is 358 grams of water. My solution is 378 milliliters. So all I did was I'm just organizing it. And now I'm gonna need more space to do the calculations. So this is what we're looking for. So let's go ahead and copy this. Let's go ahead and give ourselves a little bit more space. And let's go ahead and do the problem here. So we got that, and we got that. So this one. So this one we don't need anymore. So the one we need is this one. So that's what we're going for. We're going to calculate molality, mole fraction, and parts per billion for those conditions. So molality, let's start with that. Molality is the same as the moles of the solute over the kilograms of the solvent. So this is the only one where you are not dividing by the solution. So this is the exception to the rule. So moles of the solute divided by the kilograms of the solvent. So the solute is 28.4 grams, and we're gonna need the moles, right? We have the formula. So that's gonna be 6 times 12 for carbon, 1 times 12 for the hydrogen, and 6 times 16 for the oxygen. It's gonna be 72. This is gonna be 12, and this is gonna be 96. 10, 9. So that's gonna be, I'm rounding, so when you do it with at least one decimal place. This is gonna be 180 grams for every 1 mole. When we do that calculation, the amount of moles that we are gonna have, I'm not gonna try to do that one on top of my head. My head is not that big. So when I do that, that's gonna be 28.4 divided by 180, which is gonna be 2 significant figures. On my case, because I did 180, 0.116. And I know I am not so concerned about your mathematical result. I'm concerned that you can show me how it's done. So that's how many moles I have. So I know the moles. So my moles are gonna be 0.16 moles. And I'm gonna divide that by the kilograms of the solvents. So I have 355 grams, but I do not want the grams because I want the kilograms, and 1 kilograms equals 1,000 grams. So this is nothing more than 0.355 kilograms. 0.355 kilograms. So the molality, by the way, molality symbol is M, just like meters, so be careful. So we're using the same symbol we use for meters to say molality, and in our case, it's gonna be 0.16 divided by 0.355, which is gonna equal 0.45 molality. So that's how we find the molality. So once more, molality is the only measure of concentration of the one we're going to study that is not solute over solution, is solute over solvent, but is moles of the solute over the kilograms of the solvent. So you definitely need to know how to go from grams to moles. You need to know your prefixes, and then you can do that. So that's how we find the molality. So molality is done. So let's do now the mole fraction. So mole fraction is going to be represented by a funny looking X. It looks like a giant X. I imagine it's come from Greek, right? And that's going to be nothing more than the moles of the solute over the moles total. So that's going to be basically the moles of the solute over the moles of the solvent plus the moles of the solute. We already have the moles of the solute from the previous one. So how do we find the moles of the solvent? Well, we have 355 grams of water. The molar mass of water is 18.0 grams. So how many moles do we have? We're going to have 355 divided by 18, which is going to be at three significant figures, 19.7 moles of the solvent, which is water. So our mole fraction is going to be 0.16 moles of the solute over 0.16 moles of the solute plus 19.7 moles of the solvent. And that's going to give us 0.16 divided by 0.16 plus 19.7, which is going to equal 0.00806. And it's a mole fraction. You're dividing moles over moles, so there are no units. The moles do cancel. So 8.06 10 to the minus 3. That's our mole fraction. So that's how you find the mole fraction. Moles of the solute over the total moles, which are nothing more than the moles of the solute plus the moles of the solvent. What about parts per billion? Parts per billion is calculated exactly the same way as you do percentage, but instead of multiplying by 100, you multiply by 10 to the 6, which is by 10 to the 9, which is a billion. 10 to the 6 would be a million. So parts per million, you're going to multiply by 10 to the 6. Parts per billion, you're going to multiply by 10 to the 9. So it's nothing more, and we're going to use, if it doesn't say, we are going to assume it's asking for the mass for the mass ratio in terms of billion parts. So the mass of the solute is 28.4 grams. The mass of the solution is 28.4 grams plus 355 grams. So that's going to be 28.4 divided by 28.4 plus 355. When we do that, we get 0.0741. That's just the ratio. So what about parts per billion? 0.0741 times 10 to the 9. So how many parts per billion we have? 7.41 times 10 to the 7 parts per billion, which is a huge number. So that's how much of this carbohydrate, CCH12O6, you're going to have dissolved in 355 grams of water. It's a big, relatively big concentration. We usually use parts per billions and parts per millions most of the time for when the amounts are really, really, really small, like arsenic in water. Because a really super small amount of arsenic in water or lead, for example, can be very toxic for the population, and we have to be able to measure at those small amounts. For something like that, even though we did it in part per billion, it's not too practical to do it for something like that. Tends to be used more for metals in drinking water and gases and stuff like that. So that's how we do that problem. So this is your daily work. So your daily work is going to be you are giving glucose again. You got the same amount of water, and now you are doing percent, which you know how to do, and you're doing parts per billion, which you know how to do, and you're doing molarity that you learn how to do in Chem 1411. But just a quick review: molarity is going to be moles of the solute over liters of the solution. Percent by mass is going to be mass of the solute over mass of the solution times 100. And part per billions is going to be the same times 10 to the 9. So that's your daily work. Another problem. So let me show you first the table bigger so you can see it better. So that's what we have on this table. Basically the formulas. Molarity is this formula. Molality is this formula in terms of the solute and the solvent. Mole fraction, amount of solute in mole, total amount of the... So basically everything that we have been discussing, you got parts per billions, part per millions, part per billions, percentage. You can do the same thing with you're doing it with the mass. You can also do it with the volume. And mole percentage is same as mole fraction, but you multiply by 100. So the one we're going to use the most is going to be the mole fraction and the molality. So what is this problem asking us to do? An aqueous solutions contain 36% hydrochloric acid by mass. So the total mass of the solution is, out of the total mass, 36% is only hydrochloric acid, the rest is water. Calculate the molality and the mole fraction. So the first thing we have to do is to understand what the problem is telling us. The problem is telling us that 37% of the mass is hydrochloric acid. In other way, it's telling us that if the solution mass is 100 grams, that would be the solution, then only 36 grams are the solute, which is hydrochloric acid. So 36% is just a ratio. So let's assume, to make it easier on ourselves, that we're dealing with 100 grams of solution. So based on that, all the molality, the molarity, all those are ratios. So they had to duplicate this ratio. It doesn't matter that if we have 500 grams, we can say that based on percentage, we only have 100 grams of the solution and 36 grams of the solute. So how can we translate that to molality? Where molality equals moles of the solute over kilograms of the solvent, right? So we're saying that we have 36 grams of HCl based on the percentage, right? And you know how to find the moles, right? 1 mole over 36.5 grams. So Cl is 35.5 and hydrogen is 1. Double check that on the periodic table. I may be off by 1, but I'm going for the procedure. So once you do that, you can find the moles. And I'm not going to do it, you know how to do it. So you will have the moles of the solute. So how do we find the kilograms of the solvent? The problem doesn't give me kilograms of the solvent anywhere or the mass of the solvent anywhere. Well, it does, because it's telling me that the total mass of the solution is 100 grams, because we are assuming percentage, right? But I know that the 100 grams is solute plus solvent, right? That's the definition of solution. And I know that the solute is 36 grams. So my solvent is going to have to be 64 grams, because this had to give me 100, right? That's what I said, 100. So I have 64 grams of the solvent, which is nothing more than 0.064 kilograms. And I know you learn on Chem 1 how to go from grams to kilograms. So how do I find then my molality? Well, my molality then is going to be the moles of HCl that I found there divided by 0.064 kilograms of water. And that will give me my molality. What about the mole fraction? Well, the mole fraction, let's review this again. The mole fraction is the moles of the solute over the moles of the solute plus the moles of the solvent, right? The moles of the total moles of the solution. We know that we have 100 grams of solution, which is given by 36 grams of HCl plus 64 grams of water. So all I have to do is 36 grams of HCl, change that to moles. You know how to do that. 64 grams of water, change that to moles of water. You know how to do that also, and then just put the moles of HCl over the moles of HCl plus the moles of water. And that will give you your mole fraction. So remember, the only thing we have to learn from this problem, because you know how to do moles, you can plug in on the formula for concentration, is that the percentage is giving us a lot of information. Whenever you're doing percentage, you're immediately gonna say, oh, so I have 100 grams of solution. And out of those 100 grams of solution, 36 grams on this case is hydrochloric acid. And from there, then you can start playing with the definition of solution and find out the solvent, and then you can take it from there. So that's how we do that problem if we begin with a percentage. So here's your daily work 14.7. You are given a percentage, and you have to calculate the mole percent and the molarity. Remember, the mole percent is right here. So this is how you're going to calculate the mole percent amount of the solute in moles over the total amount of solutes and solvent times 100. It's the same as mole fraction, but multiplied by 100. That's the only difference. In addition to that, you're going to be working with molarity. And you know molarity is moles of the solute divided by the liters of the solution. So that's your 14.7. And then you're going to have 14.8, a little bit more complicated, but I have total confidence you can do it. And with that, we finish this section of chapter 14. So pending more practice, right? You can calculate the concentration of a solution. You know it's going to be, usually is amount of the solute divided by amount of the solution, except for molality, where it's moles of the solute over kilograms of the solvent. Molarity is going to be moles of solute over liters of solution. We just talked about molality. Mole fraction is moles of solute over the moles of solute plus the moles of the solvent, or total moles. And then you can find the percent composition by mass or by volume. Percent would be multiplied by 100. Parts per million is multiplied by a million, or 10 to the 6. And parts per billion is multiplied by a million, or 10 to the 9. And you should be able to convert from one to the other, like we did percentage to molarity, we did percentage to molality, and we even did percentage to mole fraction. So we covered everything that we needed to cover. So make sure you practice this. This is not the hardest part in terms of calculation, because that's coming up now with colligative properties, but the beginning to that. You cannot do colligative properties unless you can do molality and mole fraction. And that's what we're going to start next time. So until next, see you later. Stay warm, stay safe.